Okay, so we're going to have a look today at pH and indicators, which is chapter 18 of the Folan's textbook, looking at pH and indicators. It begins by looking at the topic of self-ionization of water. And I suppose basically this, we have to have chapter 17 done before we look at this. Chapter 17 looking at chemical equilibrium, and then looking at what the breakup of water is, and how that leads to identifying pH. So what self-ionization of water is basically when water can break up or dissociate. We come across this word dissociate quite a lot with when we're looking at this chapter. It breaks up slightly to form the ions, and this is the expression for the self-ionization of water. You've got water breaking up, and you've got this kind of a forwards backwards reaction symbol, reversible reaction symbol here. And you get H plus ions and you get OH minus ions. And if you were to do the equilibrium constant for this reaction, you would write it like this: Kc is equal to H plus ions in square brackets by OH minus ions in square brackets all over the H2O. This would be the equilibrium constant for this reaction, which is a reversible reaction. And what we then do is we kind of cross multiply. So we multiply the H2O by the Kc, and you get this value here, which we're calling now, we call Kw, which is the ionic product of water. So basically, Kc is a constant value at a certain temperature, and H2O concentration is a constant value. So we get this value called Kw, the ionic product of water, and that gives us H plus concentration by the OH minus concentration. So some very important points to note here: that the expression for the self-ionization of water is the breakup of water into its ions, and then the equilibrium constant would be this, giving us the Kw, which is this. And just to get that into numbers, then I suppose the Kw is measured, it can be measured at 25 degrees. It's found to be 1 by 10 to the minus 14. Now, if the Kw is the K is the concentration of H plus ions multiplied by the concentration of OH minus ions, then you could say that you put them equal to each other here, that the H plus concentration by the OH minus concentration is equal to the Kw, which is 1 by 10 to the minus 14. Now, the other thing about it is when you're looking at water, the H plus concentration is equal to the OH minus concentration. So you could substitute in, instead of H plus concentration, you could put in OH minus concentration, or instead of OH minus concentration, you could put in H plus concentration. So in this case, we're going to basically slot in, instead of the OH minus concentration, put in another H plus concentration, because they're the same, remember, in water. So if you slot in the same, you get H plus concentration squared is equal to 1 by 10 to the minus 14, which is the Kw. So if you want to find the H plus concentration, use square root both sides. Square root that and square root that. And that'll give us the H plus concentration being the square root of 1 by 10 to the minus 14. And when you calculate that out, you get 1 by 10 to the minus 7. So that is the concentration of the OH minus ions, or the H3O plus, which is another way of writing the H plus concentration. Okay, sometimes H plus concentration is written as H3O plus. So that is what we have there, 1 by 10 to the minus 7. Okay, and this is how you basically calculate out the H plus concentration in the ionic product of water. And this shows you where pH comes from. There's a few things here that you might be familiar with. You know, I suppose you might be familiar with the idea that, pH is a measure of the H plus concentration. You might remember when we looked at acids and bases previously, we said that acids dissociate in water to give H plus ions. So Obviously, if we can figure out how much H plus ions there are, you can find out how acidic something is. And we also learned that bases are something that dissociate in water to give OH minus ions. So again, if you can find out the OH minus concentration, you can find out how basic something is. The other thing that you might notice is that you probably already know that the pH scale goes from 0 to 14, and well, the KW here has a 14 in its number, and you'd know that the pH of water is 7, and you can see here that the concentration of both the H plus concentration and the OH minus concentration is 1 by 10 to the minus 7. So that's kind of where the pH values come from. 7 and 14, where water 7, the whole thing is 14. But we'll be getting to that in a little bit anyway. Just to finish up then and see how this kind of adds up. So at 25 degrees, it's important to note that it's at 25 degrees. The Kw of any aqueous solution will equal 1 by 10 to the minus 14. So the H plus concentration and the OH minus concentration must equal 1 by 10 to the minus 14. So if the H plus concentration goes up, the OH minus concentration must go down, so that the product of the two is still 1 by 10 to the minus 14. So then there's three different possibilities in an aqueous solution. You have in a neutral solution, which we just saw there, where the H plus concentration is equal to the OH minus concentration, and they're both 1 by 10 to the minus 7, and you get 1 by 10 to the minus 14 total. In an acidic solution, you'll have the H plus concentration being greater than the OH minus concentration. Again, you multiply the two together, you get 1 by 10 to the minus 14. And as you can imagine, the third one is a basic solution where the OH minus concentration is greater than that of the H plus concentration. So again, multiply the two together, you get 1 by 10 to the minus 14. But these are the three kind of situations where you have neutral, acidic, or basic solutions. And that's where we see the ionic product of water and the acidic and basic conditions. So just to have a look at a couple of exam paper questions, you can see here in 2008, you can see that it came up, write an expression for the self-ionization of water for 5 marks. That was just writing out the equation, H2O, the reversible reaction symbol, H plus and OH minus. 3 marks for writing on the formula, 2 marks for balancing it. Got you 5 marks in 2008. And then define Kw. This has come up a couple of times. Define Kw, the ionic product of water. And then they also tell us the value of the Kw, 1 by 10 to the minus 14, and show that the pH of pure water is 7 at 25 degrees C. So for 12 marks, all of that. So you can see here in the marking scheme that they go through the idea that Kw, I suppose, basically writing the Kc for this equation first, then finding out that the Kw is the H2O concentration times the Kc, which is also equal to the concentration of H plus ions by OH minus ions. That's what they have here for 3 marks. And then going forward to suggest that OH minus ions are equal to H plus ions. So you can substitute one in for the other. So if you've got your H plus concentration squared, you can put it equal to your 1 by 10 to the minus 14. And then you can square root both sides and you'll get the H plus concentration equal to 1 by 10 to the minus 7. So that's as far as we've gone so far. And you get 9 of the 12 marks for writing all that down. We haven't gone into how to find the pH yet, just a simple formula there at the end for the last 3 marks. And then just have a look at this question from 2019. You can see that here in part B, they talk about pure water self-ionizing to give us the H plus concentration, H plus ions and OH minus ions. They give us an ionic product of water table here on the right, showing us different temperatures and different kWs. But the part I want to kind of focus on here is just the first part here. Write the self-ionization constant kW expression for water. And you can see that there are 12 marks going for part 1 and part 2. Turns out that there's 6 marks going for this part 1. And if we look at it here, you can see there that the Kw is equal to the H plus concentration by the OH minus concentration. And there was 6 marks going for it. Important to note that, you know, they took away 3 marks if you didn't include the square brackets. So that's how important the square brackets are. Even if you put them in as round brackets, it says deduct 3 marks for brackets not square. So very important that your brackets are square. And if you included H2O, they'd still allow 3 marks. But Kw is equal to H plus concentration by the OH minus concentration.